Alright, this video is for anyone who wants a little bit more help with some of the independent practice or the homework when doing percent yield. So if you go to the percent yield handout and homework, we're starting with part 4, independent practice. The directions here for part 4 are that for each problem you should write and balance the chemical equation, show all your work, identify the limiting reagent, calculate the theoretical yield, and compute percent yield. I want to see all the work, and I want you to box your final answers. So let's go ahead and get started with number 1. Number 1 says, zinc metal reacts with hydrochloric acid to produce zinc chloride and hydrogen gas. All right, so we've got zinc metal, that's Zn, reacts with hydrochloric acid, which is HCl. And it produces zinc chloride and hydrogen gas. Now, if you were unsure about zinc chloride, what you could have done is you could have said, okay, well, zinc, we know, always has a positive 2 charge, and chlorine always has a negative 1 charge, and we can crisscross to get our zinc chloride. Great. Moving on here, we need to make sure that we balance our chemical equation. We've got 1 zinc over here, 1 zinc over here, 1 hydrogen over here, 2 hydrogen over here, 1 chlorine over here, 2 chlorine over here. So the way we'll balance that is by putting a 2 right here. All right, so once we have a balanced chemical equation, what I like to do is I like to write underneath what I am starting with. So in this case, we are starting with 18.5 grams of zinc, and we're reacting it with 15.0 grams of hydrochloric acid. And so the first thing we have to do is calculate the limiting reagent. And the limiting reagent calculation is going to allow us to calculate a theoretical yield. And that theoretical yield is going to allow us to find the percent yield. So let's do that piece by piece here. So first, I'm going to start with my zinc. And I'm going to say, okay, zinc, we've got 18.5 grams of zinc. And I want to convert that into how many grams of zinc chloride I can get out of that. And the way that we're going to do that is by using the molar mass. So let me get the molar mass of zinc real fast. Maybe. Okay. We've got 65.38 grams of zinc in 1 mole of zinc. And for every 1 mole of zinc, we get 1 mole of zinc chloride. And how much will that 1 mole of zinc chloride weigh? Well, we'll need the molar mass for that. And I'll do that by saying, well, the mass of zinc is 65.38 grams per mole, and I only have 1 of those. And I've got 2 chlorine, and chlorine's molar mass is 35.45 grams per mole. And so let me grab my handy dandy calculator. And we've got 65.38 plus 2 times 35.45. And we'll get 135 36.28 grams of zinc chloride. All right. So now we'll plug that into our calculator. And what I'm doing is 18.5 divided by 65.38 times 136.28. And I'm getting 38.6 grams of zinc chloride. Great. Let's try the same thing for our hydrochloric acid. We start off with 15.0 grams of hydrochloric acid, and 1 mole of hydrochloric acid is going to be the mass of chlorine, 35.45 grams, plus the mass of hydrogen, 1.01 grams. And so we'll get 36.46. And so 36.46 grams of hydrochloric acid in 1 mole of hydrochloric acid. From there, we'll say, well, for every 2 moles of hydrochloric acid, we get 1 mole of zinc chloride. So for every 2 moles of hydrochloric acid, we get 1 mole of zinc chloride. The reason why I'm putting moles of hydrochloric acid in the bottom here is so that it is canceled out with moles of hydrochloric acid up here. All right. Then, for every 1 mole of zinc, I'm sorry, this is a 2ZnCl2. For every mole of zinc chloride, we get 136.28 grams of zinc chloride. So I'll plug that into my calculator. I've got 15 divided by 36.46 divided by 2 times 136.28, and I will get 28.0 grams of zinc chloride. Great, so my hydrochloric acid then is going to be my limiting reagent, right? This is how much zinc chloride I can make with my 15 grams of hydrochloric acid. Great. And then my problem says that the student only collects 17.8 grams of zinc chloride. And so that's when we do our percent yield calculation. Our percent yield is going to be the part over the whole times 100. Or another way to say that is our percent yield will be what we got experimentally over what we should have gotten theoretically, according to our math, times 100. And so we'll say, well, the student only got 17.8 grams of my zinc chloride, 17.8 grams, but they should have gotten 28.0 grams. And so when we do this calculation, we should then get 17.8 divided by 28 times 100. We get 63.6% yield. Great. All right, so let's read the question again, make sure we did everything that we were supposed to do. We were supposed to identify the limiting reagent. Great. Hydrochloric acid is the limiting reagent. We were supposed to calculate the theoretical yield. We did that. Here's the theoretical yield. Theoretical yield in this case will be the yield of product that we get from our the the smaller yield of product we get, right? It'll be the yield of product we get from our limiting reagent. And then we needed to calculate our percent yield, which is the experimental over the theoretical. Experimental over theoretical times 100, and we have 63.6%. Great, we can go ahead and move on now to question 2, and we'll probably go through the next one a little bit faster. Because we took 10 minutes to do just that first one. All right, question 2. We have copper 2 oxide reacting with hydrogen gas to produce copper metal and water. So what we're going to do is we're going to do copper 2 oxide. For those of you who are struggling a little bit with that, remember the Roman numerals indicate the charge of the cation. So we got copper 2 oxide. So when we crisscross, we'll get CuO. Right? So we got copper 2 oxide reacts with hydrogen gas to produce copper metal and water. Great. The first thing that we're going to do then is we're going to make sure that everything's balanced. We got one copper here, one oxygen here, one oxygen here, one hydrogen, diatomic hydrogen molecule here, and one diatomic hydrogen here. Another way to say that is two hydrogen, right? Perfect. So we're already balanced, and we're good to go there. So we can just move on. This says that 32.0 grams of copper 2 oxide reacts with 2.50 grams of hydrogen gas, and that the reaction yields 22.1 grams of copper metal. So the important thing with that is we know which product we're going to try to get because that's the one that we're given, right? We want to find the percent yield of copper. So we need the theoretical yield of copper, and we need stoichiometry to do that. So let's start with the copper oxide. We are starting off with 32.0 grams of copper oxide, copper 2 oxide, and we need to convert this into moles and then use that to determine the amount of copper that's there. So the molar mass of copper is 63.55. It's 63.55 grams per mole, and the molar mass of oxygen is 16.00. So when we add that up, we get 79.55 grams of copper 2 oxide in 1 mole of copper 2 oxide. All right, for every 1 mole of copper 2 oxide, we get 1 mole of copper. And 1 mole of copper weighs 63.55 grams. All right, so this is the mass of copper we can expect if we start off with 32 grams of copper oxide. Great, so let me plug that into my calculator. I'm doing 32 divided by 79.55 times 63.55, and I'm getting 25.6. 25.6 grams of copper. Let's do the same thing now with hydrogen. 2.50 grams of hydrogen. We'll convert that into moles. 1 mole of diatomic hydrogen is equal to 2.02 grams of diatomic hydrogen. For every 1 mole of H2, we can expect to get 1 mole of copper, and 1 mole of copper weighs 63.55 grams. We got that number from right up here. So we plug that into our calculator. We've got 2.50 divided by 2.02 times 63.55, and we get 78.7 grams of copper. Excellent. So this here is going to be our limiting reagent by far, right? 25.6 grams is our theoretical yield. Percent yield is the actual or the experimental over the theoretical times 100. Our problem, if we go back to our worksheet, it says that we get 22.1 grams of copper in our experiment, but we should have gotten 25.6 grams of copper. And so when we plug this into our calculator, we get 22.1 divided by 25.6 times 100, and we'll get 86.3%. Not too shabby. All right, hopefully this is making a little bit more sense to you. Let's keep on going. Next up, we've got a student performs the reaction N2 plus 3H2 yields 2NH3. And they achieve a percent yield of 68.4%. All right, we're given a couple of other bits of information too. We're given that we start with 28.0 grams of diatomic nitrogen, and we start with 9 grams of diatomic hydrogen. We also get that the student reports having 11.6 grams of product. So the first thing that we want to do is we want to identify the limiting reagent and calculate the theoretical yield. And then we want to verify the student's reported percent yield using our own theoretical yield. Okay. So what that means is that we're doing everything that's the same as before, but we're just saying, hey, is the student right in their calculation here? Was the student correct in their calculation here? And if the answer is yes, then awesome. If the answer is no, then we want to identify the likely source of error. Great. So let's go ahead and get started. We'll start out with the nitrogen, 28.0 grams of nitrogen. We'll convert that to moles of nitrogen. Molar mass of nitrogen is 14.01 grams. Let me double check that. Looks like 14.01, and it's diatomic, so we'll have 28.02 grams of nitrogen in 1 mole of diatomic nitrogen. For every 1 mole of diatomic nitrogen, we get 2 moles of NH3. All right, and then 1 mole of NH3 is going to weigh a certain amount, right? We'll do that by saying, okay, well, nitrogen is 14.01 grams per mole, hydrogen is 1.01 grams per mole, and there are 3 of them. And so we should get 17.04 grams per mole. Alrighty, We'll plug this into our calculator. I am doing 28 divided by 28.02 times 2 times 17.04, and we're getting 34.1 grams of NH3. Let's do the same thing with the hydrogen now. 9.00 grams of hydrogen gas. We convert that to moles. 1 mole of hydrogen gas is 2.02 grams. For every 3 moles of hydrogen gas, we get 2 moles of NH3, and then 1 mole of NH3 is 17.04 grams. Great. And so we'll plug that into our calculator. 9 divided by 2.02 times 2 divided by 3 times 17.04. And we will get 50.6 grams of NH3. All right, our percent yield calculation is going to be the experimental over the theoretical times 100. What is our experimental here? Do you remember? It tells us in the problem what our experimental is. It says that the student reports collecting 11.6 grams of NH3. And what's our theoretical yield here? Our theoretical yield is going to be this guy, 34.1 grams. So we plug this into our calculator. We can already see that there's a problem here. Right, we're getting 34%. So does the reported percent yield match our calculation? It doesn't. It doesn't. What might be the reason for this? I want you to sit and think about this for a second. Go ahead and take a minute to do that. All right. Hopefully you paused the video. Hopefully you've taken a little bit of time to consider this. A couple of different things may have occurred here, and I would have accepted a plethora of answers if they're well reasoned. One of the things that may have happened is that the student only used nitrogen, just N, instead of N2. Right? What that would have done here is that would have halved the amount, which would have artificially doubled the product here. And that could have caused an error. What's more likely, though, is that the student didn't do the mole ratio. That's more likely. That they forgot the 2 moles of NH3 here. Great. There's another one that you may have said. You may have said is that you may have treated this one as the limiting reagent instead, which could produce a weird response. I don't know if it would give you this number. But it could have given you a similarly weird response, right? So that's what I would suggest. Probably that the student forgot the mole-to-mole ratio here. Alrighty. Let's keep on trucking, shall we? Let's say the exit ticket. Two students run the same reaction. Student A reports a 96% yield, and student B reports a 61% yield. Their teacher gives student B a higher lab grade. In 3 to 5 sentences, explain a scenario in which this would be the right decision. Well, if you were following along with the notes from earlier, you may remember that it's not always the case that you want a high percent yield. There are certain reactions that actually will produce low percent yields naturally. This is especially true of reactions of very large molecules. It's also true of reactions that are that have metal as one of their, like a solid metal, as one of their reactants, because in order for the reaction to occur, you actually need one atom to touch another atom, or one molecule to touch another molecule. Okay? So it may be the case that student A actually did not give the right percent yield, that they gave one that was way too high and lied, or maybe they did something wrong. Maybe you should assume the best. They may have just had an error. Maybe their substance wasn't dry enough, or whatever the case may be, and student B would receive a higher grade because 61% is closer to the accepted value of the reaction yield. So any of those things could be true. Let's take a look at the homework now. Same thing as before. We want to write and balance the chemical equation, we want to identify the limiting reagent, we want to calculate the theoretical yield, and we want to calculate the percent yield. So let's look at this guy. Silicon dioxide reacts with carbon at a high temperature to produce silicon carbide and carbon monoxide gas. Okay, this is a little bit more tricky. So silicon dioxide is SiO2. And we're saying that it reacts with carbon. Okay, this is going to produce silicon carbide and carbon monoxide gas. All right. So, first things first, we have to balance. It's a bit tricky to balance, but that's okay. We got silicon, one here, one carbon here, one carbon here, 2 oxygen here. Oh shoot, we've got, oh, I misspoke, I'm sorry. We've got one silicon, one carbon, 2 carbon, 2 oxygen, 1 oxygen. So what I'm going to recommend doing is probably trying to, because the carbon is by itself over here, we can put almost anything in front of it, right? And so what we should probably start off with is making sure that oxygen is balanced. So we look at oxygen, there's 2 here, 1 here, we'll put a 2 right there. When we do that, that tells us that we now have 3 carbon on this side, and we can put a 3 over here, and that will balance our chemical equation very nicely. Great. Now we need to identify the limiting reagent. And what I like to do at this point is I like to just write underneath how much I'm starting with. So I'm told that we have 30.0 grams of silicon dioxide and 20 grams of carbon. Awesome. So we'll do silicon dioxide first, shall we? We've got 30.0 grams of silicon dioxide. And we're just going to do the same thing that we've been doing, just some stoichiometry. We want to determine how much silicon carbide we're going to get at the end. And so we have to convert from silicon dioxide, grams of silicon dioxide to moles of silicon dioxide, compare moles to moles, and then get this out of moles and into grams. So we will say 1 mole of silicon dioxide is going to be, let's see, looking up the molar mass of silicon right now. Okay, 28.09 grams per mole. And then we'll add that to oxygens, and there are 2 oxygen. So let me grab my calculator, and we're doing 28.09 plus 16 times 2. And we will get 60.09 grams of silicon dioxide. And then we can do a mole-to-mole conversion. 1 mole of silicon dioxide gives us 1 mole of silicon carbide. And then we can convert that to grams by saying 1 mole of silicon carbide weighs 28.09 grams per mole, plus, that's silicon, plus carbons, which is 12.01 grams per mole. All right. That should be 40.10. All right, we plug that into our handy dandy calculator. We get 30.0 divided by 60.09 times 40.10. And we get 20.0 grams of silicon carbide. Now we'll do the same thing, but with carbon. We're starting off with 20 grams of carbon. All right. 20 grams of carbon. We're going to convert that to moles. We've got 12.01 grams of carbon and 1 mole of carbon. For every 3 moles of carbon, we get 1 mole of silicon carbide. And then 1 mole of silicon carbide weighs 40.10 grams. And we'll grab our calculator, and oh, I forgot to put the 0.0 there. All right, we'll do 20.0 divided by 12.01 divided by 3 times 40.10 gives me 22.3 grams of silicon carbide. Excellent. Excellent. So the next thing we have to ask ourselves is, what's the percent yield? And we can do that fairly easily. We can say that the percent yield is equal to the experimental over the theoretical times 100. And so, let's see, we were told that we got 14.8 grams of silicon carbide, but we could have gotten up to 20. And we'll plug that into our calculator. And we should get a 74.0% yield. Awesome. Hopefully these are starting to feel a little bit easier. All right. So I don't want to beat a dead horse with some of these problems. We've already been at it for over 30 minutes. So let's move to maybe a slightly harder problem. Let's move to problem 4 here. Let me just grab a new sheet of paper. All right, this says that butane burns in oxygen, and that a lighter contains 5.82 grams of butane, and the flame consumes 20.8 grams of oxygen. Analysis of the exhaust shows 13.6 grams of carbon dioxide and 6.20 grams of water were collected. The first thing that we want to do is write and balance the complete combustion equation. We'll identify the limiting reagent. We'll calculate the theoretical yield of both carbon dioxide and water. And then we will calculate the percent yield for each product. the percent yields for CO2 and H2O will be different, and so we want to propose a chemical explanation for why the two products might be collected at different efficiencies. Ooh, oh man, this is a bit of a challenge, but I think we can do it. So, let's begin. First thing we want to do is our chemical equation. We have C4H10. And we're told that it's a combustion reaction. Combustion reactions are always a hydrocarbon plus oxygen produces carbon dioxide and water. Now, the hardest thing to take care of when we're balancing combustion reactions is the oxygen. And the reason for that is because on the left-hand side, it's always 2, O2, and on the right-hand side, it's always 2 plus 1, 3. And so that's always a bit of a hassle. And so what I advise doing, and I'm going to grab a pencil just in case I make a mistake here, what I advise doing is starting with the hydrogen and the carbon, and then going back and seeing if you can make the oxygen work. So, you might not be able to see this very clearly, but hopefully you can. There's 4 carbon here, 1 carbon here. I'm going to put a 4 here. And there's 10 hydrogen here and 2 hydrogen here, so I'm going to put a 5 here. Hopefully you can see that. And now I've got 2 times 4 oxygen, 8 plus 5 oxygen, 9. Shoot. So when that happens, we can't come over here and say 4.5 O2 to get to 9, because we can't have half an oxygen molecule. So what we have to do is we have to double everything. We have to put a 2 here, which will give us, I'm sorry, I miscounted that. This was 8 plus 5 is 13. My apologies. We got to double this guy to 8 and double this guy to 10. And so now we've got 10 plus 8 times 2. So we got 16 plus 10, that's 26. Half of 26 is 13. Alrighty. Hopefully you did that fairly easily. So the next thing we have to do here, I'm going to go ahead and write over this in marker to make it easier to see. The next thing we need to do here is identify the limiting reagent. Okay. So at this stage, it doesn't really matter which product you go to. However, when we calculate the percent yield for each product, once we find out what the limiting reagent actually is, we will have to find how much carbon dioxide the limiting reagent makes and how much water that limiting reagent makes. Let me just go ahead and do the problem and see if you can follow along. I'll mention that again. I'll bring that up again once we get through the problem a little bit further. So we're told that we are starting with 5.82 grams of butane. I'm going to have us go to water, just because I know the molar mass of water better. And so I'll have to take this to water and this to water to find out the limiting reagent. But you could do either of these. It doesn't really matter. So 5.82 grams, 1 mole of butane. Well, we know what we're going to have to do. We're going to have to say, okay, we've got 4 times the molar mass of carbon, 12.01, plus 4 times the molar mass of hydrogen, 10 times the molar mass of hydrogen, 1.01.
And we'll plug that into our calculator. We've got hang on a second, my calculator's freaking out on me. All right, I'm getting 58.14 grams per mole there. All right. And now we know our molar ratio here. Remember, I said we wanted to go to water just because the molar mass there is easier, but you could do either of these things. 2 moles of C4H10 gives us 10 moles of water, and 1 mole of water is 18.02 grams. So we put that into our calculator. We've got 5.82 divided by 58.14 times 10 divided by 2 times 18.02. And we get 9.02 grams of water. Now I'll do the same thing for the oxygen. We were told that we're starting with 20.8 grams of oxygen. This one is a little bit easier. Remember, we're going to water, so we'll say 1 mole of oxygen gives us 32.00 grams. That's just 16 times 2. We also know that for every 13 moles of oxygen, we get 10 moles of water, and that 1 mole of water is 18.02 grams. So we'll plug that into our calculator. 20.8 divided by 32.00 times 10 divided by 13 times 18.02. And we get, 9.01 grams of water. All right, so it's very, very close here. Very close. We've got a razor thin margin, but it looks like oxygen is our limiting reagent. All right, so this is my theoretical value for how much water I will get, but how about the theoretical value for how much carbon dioxide I will get? Well, now that we know what the limiting reagent is, we can do that for just the oxygen. We'll say 20.8 grams of oxygen. Oops. We've got 32.00 grams of oxygen per mole of oxygen, and that for every 13 moles of oxygen, we will get 8 moles of carbon dioxide, and that 1 mole of carbon dioxide is going to be 12.01 plus 2 times 16.00. So that's going to be 12.01 plus 32. And so we've got 44.01 grams. All right. 44.01 grams of CO2. Awesome. Plug that into our calculator now. We've got 20.8 divided by 32.00 times 8 divided by 13 times 44.01. and we get 17.6 grams of carbon dioxide. Alrighty, let's keep going. What is the percent yield for each product? Well, this is the theoretical yield for water. This is the theoretical yield for carbon dioxide. If we look at our problem, we can see that we got 13.6 grams of CO2, but we should have gotten 17.6 grams of CO2, and that we got we got 6.20 grams of water, but we should have gotten 9.01 grams of water. So we can plug each of these into our calculator. 13.6 divided by 17.6 times 100, and we get 77.3% yield. And over here, 6.20 divided by 9.01 times 100 gives us 68.8%. All right. Now, this is a little bit counterintuitive. Right, this is counterintuitive because you'd expect our percent yields to be the same, but they aren't. Why? I want you to think about this. Why might we collect these products in different efficiencies? There's a bunch of different answers that I might accept here, and I probably wouldn't ask a question like this on the test. One of the best answers here is that, have you ever burned anything before? You ever burned a candle or something like that? Does it only give off carbon dioxide and water? Not usually. Usually we can expect that it's going to end up giving us a little bit of soot. Sometimes it will also give us different kinds of carbon products, carbon monoxide, for instance. Anybody who has a gas stove, a natural gas stove at home, you know that you need carbon monoxide detectors around your house in case that it starts to leak, or that sometimes if you have an imperfect combustion, it will produce quite a bit of carbon dioxide. Carbon monoxide. So these sorts of things can cause our theoretically perfect reaction to happen imperfectly. I also would have accepted that it's really hard to collect water and carbon dioxide, right? At this point, they're both gases, and collecting both of them is going to be very challenging. So you may have made an error in your collection processes. I would also say that it's possible that water may have escaped, or that it may have been, stuck on the wall of some of our apparatus or something like that. You also could have said, if you were very fancy, you could have said that carbon dioxide actually dissolves readily in water, and so we could have gotten weird results because the carbon dioxide dissolves into the water. So any of those explanations would have been fine, but again, I probably won't ask a question like that of you on a test. Excellent. Now, just for fun, we can try number 5. Gosh, I'm using a Sharpie in this room, and it's really starting to smell. What a time to be alive. So, student reacts 10 grams of aluminum with 30 grams of iron oxide in a thermite reaction. After the reaction, the student recovers 13.2 grams of iron. We want to identify the limiting reagent and calculate the theoretical yield of iron. We want to calculate the percent yield of iron. And we want the student, we say that the student also weighs the aluminum oxide produced and finds 8.60 grams, we want to calculate the percent yield also of aluminum oxide. And then we will ask, is it chemically possible for the 2% yields to be different? And how might two products from the same reaction have different percent yields? So this isn't terribly different from our question 4. What I want you to do is I want you to try this one on your own if you've made it this far and you're so inclined, and then I will perform this in just a minute. Go ahead and do that now. All right, so hopefully you've had a chance to go ahead and try this on your own. And I just want to walk you through my math here. So I first converted aluminum to aluminum oxide and found that I should have gotten 18.9 grams. And then I did the same thing for iron oxide to aluminum oxide and got 19.2 grams, telling me that aluminum is my limiting reagent. From there, what I did is I converted aluminum to iron and got 20.7 grams of iron, at which point I can find the percent yield of iron by doing my theoretical on in the denominator, and then I'm given 13.2 grams of iron in my question, finding a 63.8% yield. Same thing with the percent yield of the aluminum oxide. I got 8.60 grams when I should have gotten 18.9 grams. And I found a 45.5% yield. So the question now is, can these two products have different percent yields? And the answer is yes. This is a chemically and physically legitimate process. It's actually usually the norm rather than the exception. The reason for that is because percent yield is measuring something called collection efficiency. It's not reaction completeness. It's how well we can, or not only reaction completeness, it's also how well we can go about actually collecting these samples and measuring them, right? So percent yield is a measurement of what you can isolate and weigh, not necessarily a fixed property of the reaction stoichiometry. Yeah, aluminum oxide can form a molten slag. It can kind of like spatter all over the place, and so collecting it is actually really quite difficult. Again, I wouldn't ask a question like that of you on your test, but just getting you to think through, what is the process, what is the stoichiometry telling me, how do I calculate percent yields, things like that. That's really the focus here. With that, I hope that it was helpful and that you learned a lot. And if you have any further questions, please feel free to reach out to me and meet with me during office hours.